Okay, cool. We're going to get started. So let's, so it is recording now as well. Okay, cool. So welcome to everyone, and thank you for coming along to the first TETHYS seminar. My name's Will, and I'm co-hosting this event this evening with Safi Thorne, who's at Cambridge University. And I want to say a massive thank you to Safi as well for all of the work that she's put into to kind of make this project happen. It's mostly because of her work that it's all actually started, as well as a lot of other people from other GeoSoc communities around the UK. So thank you to everyone. So a few bits of housekeeping before we start. Each talk is going to run for about 15 to 20 minutes, and there'll be a short period for questions afterwards. If you've got any questions at any point, put them in the chat and during the talk, and then we'll read them out to the speakers at the end. If you don't want to put something in the chat publicly just because you don't feel comfortable, then feel free to message a question to Safi or to myself or privately through Zoom, and we can ask that for you anonymously. And there's also going to be a feedback survey, which I'll put in the chat for anyone who wants to get involved at the end. We're always kind of grateful for any feedback. It's a new project. So yeah, any feedback on any parts of the seminar would be really good. In terms of code of conduct and things, everyone had to sign it on when you book tickets. So videos, hopefully, please can you switch them off, just because there's quite a few people on this call and it might cause some latency issues. And as well, microphones as well, can you keep them muted unless you're invited to speak? The seminars as well, they're kind of built and designed to provide a platform for young geoscientists to present their research within a safe setting, so independent of kind of race, gender, religion, sexuality or background. And therefore we kind of want everyone to behave in a professional manner. Any actions or comments which may be reasonably considered disrespectful, discriminatory or compromise the safe and inclusive nature of the seminars is forbidden. And this includes any comments after the seminar, during questions, feedback, anything like that as well. And if there are any issues and people don't follow any of the guidelines, then we will have to kind of remove people just to make sure everything moves on smoothly. So that's my little spiel, and I won't keep talking for much longer. So I'm going to introduce the first speaker, who is Jamie Kelly. So Jamie did his integrated master's and undergraduate at Southampton University and is now doing a PhD at Southampton University looking at sediment-hosted copper deposits in Zambia and Argentina. So Jamie, if you want to share your screen. And
yeah, sure, no problem. Thank you for the introduction, Will, and thank you for putting this on. I know how much effort it can take to put these on because I've had to host some meetings myself. But yes, we'll get started with what we're going to be talking about today. And what we're going to be talking about today is possibly my favourite deposit type, despite my PhD, volcanic massive sulfide deposits. And we're going to be using an example from my master's work in 2018 in the Yilgarn Craton, Australia, called the King deposit. So this is just going to be the rundown. I'm going to talk quite a lot about just VMS in general, just for anybody out there who doesn't know what they are. If you're an undergrad studying ore deposit systems for the first time, you're going to be well up to speed, I promise you. And then, of course, talk about Yilgarn and King North geology. So VHMS systems, they stand for volcanic hosted massive sulfide systems. You may see them as volcanic massive sulfide systems in the literature or volcanic associated massive sulfide. Every geology term, there's just too many of them. So these form in extensional environments. This map just shows you the various different extensional plate tectonic settings. And obviously we get them around mid-ocean ridges, mid-Atlantic ridge, East Pacific ridge. You're going to find actively forming seafloor massive sulfide systems there. The classic black smoke events, which I'm sure many of us have seen, that's where we get them. But also we get them in back arc basing environments. So these environments where we have some subduction and then the upper plate is in extension, and therefore we can generate these seafloor massive sulfide systems. And it's those ones in the back arc basins that are going to be preserved in the geological record much more than the mid-ocean ridge settings, because they're in the lower plate environment. And so when they get subducted, unless you produce an ophiolite, you don't preserve them. So here's your black smoker chimney. Of course, you have the chimneys full of sulfide sort of material and also organisms. And these have been forming ever since about 3.5 billion years ago. The oldest Archaean VMS system I've come across is something in the Dresser Formation in Australia. And that's also where we get evidence for a lot of life. And so this area of research is great for anyone who's interested in the origins of life. You'll find lots of papers on that. VHMS systems are polymetallic, which makes them very attractive exploration targets. We get a lot of lead, zinc, copper, but also silver and gold. And then they're classified as exhalative type deposits, if you want to think of them as that. But how does this actually work? And this is a great diagram from a paper by a man called Alan Galley. He is like the father of VMS, if you like, essential reading. And I'm going to kind of rinse through this. But essentially what happens is we have a deep-seated intrusion that comes into kind of the shallow crustal environment. Obviously, when we're rifting, we've upwelled the asthenosphere, we're starting to thin the crust, etc. And what we're doing is we're starting to heat up any pre-existing seawater within that volcanic strata, and that's going to essentially begin circulating, and it's going to start to vent to the seafloor. As this system evolves, what we end up doing is obviously forming these synvolcanic faults and fractures within the rift environment. We can draw down seawater, that then starts to heat up, it reacts with the raw rocks that are within that particular environment, and what that's going to do is essentially start to make the originally alkaline fluid acidic. And once it becomes acidic, it can start to strip out the metals, and the metals like zinc, copper, gold, they like acidic fluids. So once it's done that and it becomes quite superheated and it becomes quite buoyant around 300, 400 degrees Celsius, we can start to move that back up the synvolcanic faults, and we're going to begin to vent that on the seafloor. Now, once it moves up that synvolcanic fault, it's going to interact with things like seawater again. It's going to start to get cooler, and it's essentially going to shock the system. And once it does that, we reduce the capacity for that fluid to carry the metals, and that's when we get the deposition of those sulfides at or near to the seafloor. And that's where we form these sort of lens-shaped massive sulfide bodies, some veining. And in the last sort of part of the diagram, that's just the general structure of an evolved hydrothermal system, where it's kind of the sort of subvolcanic terrain is kind of separated from the upper part by this silicification, which is an impermeable barrier. And that's where we're forming the massive sulfide deposits. Now, what we can get at times is if we can penetrate that silicification again with a new intrusion and start a new sort of hydrothermal cell, then that's when we can get stacked VMS deposits. And so the best VMS targets in the world often have multiple horizons of sulfide lenses to be explored. And you'll see that time and time again in the Abitibi province in Canada, and also parts within Australia, and maybe even within some of the VMS systems within Sweden. So this is just a cross-section, another classic diagram. This one gets used a lot, just sort of depicting what a sort of sulfide mound looks like. This is based on the TAG hydrothermal system. Essentially at the core, it's kind of heavily silicified. We get a lot of chlorite there, and then we kind of grade outwards in terms of the alteration into more sericite and eventually into more carbonate. And then the sulfides themselves at the center tend to be more copper rich, based on essentially the heat of the fluid. And then they grade outwards more to lead, zinc, and potentially barite as well. And there's just a summary of essentially how it works there again. So when we're classifying VMS deposits, we don't actually classify them based on the metals, we classify it based on the lithology. And what we have is 6 different types of VMS deposit. So these traditionally were named after the type localities. So where you see in the literature these names, it just equates to the classification you see on the left here. So the first type we get is mafic dominant. These are ones that form mainly at mid-ocean ridge settings. We don't have a lot of felsic rocks. We don't have a lot of sediment rocks, and the ore bodies are hosted within the mafic volcanics themselves. These get preserved mainly as ophiolites, so we tend to see them in the younger rock record than the older rock record, but they often contain a lot of copper, a lot of zinc, sometimes gold. When we get into the bimodal systems, they tend to be associated more with the arc rifts. So the sort of more incipient arcs, they tend to form the bimodal mafics, where the more evolved the arc is when we start to rift, we have more felsic rocks, and they're called Naranda type and Kuroko type. You'll see that in the literature. Naranda in Canada, Kuroko's in Japan. And then the siliciclastic, felsic, and politic mafic, that's when we start to get essentially a rifted basin that's already had a good input of sediment into it. So again, they tend to be quite evolved. Often rifted continental arc settings tend to form these. And then lastly, we have this random one, which is a hybrid between a sort of high sulfidation epithermal gold system and a VMS system. And it's thought that a lot of the modern environments right now are forming these types of deposits. But in the geological record, I think the one standout example of this is an example called Eskay Creek. It used to be the richest gold mine in the world when it was in operation. It's well worth a study if you're interested in these systems. So I talked about alteration. Now, the alteration is going to be quite important when I talk about my stuff later on, so I thought I'd define it quite clearly here. Obviously, we have a lot of different alteration sort of environments, but the ones of interest, or the ones that we really want to be finding when we're exploring, is the hanging wall alteration and the footwall alteration. The footwall alteration is usually more intense. It's where we see the loss of those alkali metals, an addition of sulfur, and this enrichment in aluminium. Whereas the hanging wall alteration is quite extensive, but less intense. And sometimes we do see the footwall alteration sort of percolate into the hanging wall alteration, but really it's the footwall that if we find that, we're pretty proximal to where the sulfide lens is going to be. And here is a table of those various minerals that you might want to find and its relationship to the metamorphic grade. Because when we're dealing with Archaean or even Proterozoic ore deposits, they've underwent a lot of deformation and it's quite likely they're going to be metamorphic. So it's quite, and depending on the metamorphic grade, we change ever so slightly, in some cases, sometimes a lot, the ore minerals, or essentially the alteration minerals we see. So really the ones of interest are chloritic, cericitic, and carbonate propylitic. Argillic and advanced argillic, I'm not really going to be talking about too much. So it's just bear in mind what those are. And there's just a summary. You can find this in the classic Lawrence Robb book, I think page 165 or something like that. It's a good diagram for just essentially summarizing how VMS works and a few of the properties of the fluids. And there's an example again in a recent sort of book by a guy called Hannington, showing you that obviously we get this copper-rich mineralogy kind of at the center of the deposit, and it grades outwards to zinc and lead. Underneath this mound or lenticular-shaped sulfide body in the sort of stockwork, we have chlorite alteration and cericitic alteration. So VMS through time, here, this is quite an interesting observation I found when doing my master's work, is that a lot of the VMS deposits cluster in distinct peaks, and these peaks tend to associate themselves with supercontinent cycles. So the peaks that are kind of here, that's in relation to a supercontinent known as Kennerland. Then in here, around the 2000 mark, that's Nuna. Around the younger one is obviously Pangaea. Now, the one peak we don't see is Rodinia. And I don't really have a great explanation for this, but I did ask this to somebody who is much more knowledgeable than I am. And they explained that the Rodinia tectonics were slightly different to the other tectonic regimes, in the sense that the upper plate was not so much in extension when we had collision, whereas the others, it's thought, were much more in extension, had the ability to form these back arc VMS deposits. So if you was wondering why there's no peak there, that's the best explanation I have. Now, when it comes to Archaean age VMS deposits, we tend to basically find that the VMS associated with juvenile crust. Now, juvenile crust and evolved crust, I'm going to define that in a minute, but this is just a map of the Yilgarn Craton and how this pink bit here is called the Teutonic zone, and this yellow bit over here, which is called the Q zone, that is basically where we see all of the VMS occurrences in the Yilgarn Craton. Now, when you compare the deposits in the Yilgarn that are VMS and the Canadian Superior Craton, we see a very, basically they're the same age in terms of like their lithologies, both of those cratons, but the Superior Craton in Canada has way, way more VMS than what Yilgarn does. And it's thought that the reason is that the Superior Craton has much more juvenile crust than the Yilgarn Craton. And that's why as well, when we have more evolved crust in the Yilgarn, we get more magmatic sulfide deposits in those settings. And so juvenile is just defined as having a low mu, which is the ratio of 238 to 204 lead. Basically, when you extract a melt from the essentially the mantle, you're going to have a high lead content. And so when it crystallizes into lead-based minerals, it retains the isotopic source. And where we're seeing higher sort of lead and obviously low radiogenic uranium, we're going to get this low mu ratio. We get more radiogenic neodymium because neodymium is more fractionated when we partially melt than what samarium is. So basically, juvenile means low mu, and more radiogenic neodymium. Evolved just means high mu and less radiogenic neodymium. And it's those differences between those crustal sources that is responsible basically for VMS and magmatic sulfide being more prevalent. So Yilgarn then. Yilgarn Craton is separated into kind of two major terrains. We've got the Western Yilgarn and the Eastern Goldfield super terrain. The Eastern Goldfield super terrain is made up of several sub-terrains, but we're going to be focusing on the Canalpi terrain because the Canalpi terrain has this very distinct, if you like, purple zone here, which corresponds to these young depleted mantle model ages, which is where the juvenile crust is. Now, my deposit was located down here in the bottom right, kind of around this spot here, and it's called the King deposit. Now, the Canalpi terrain consists of essentially granite greenstone terrains, like a lot of Archaean age belts, but specifically it's comprised of about 2.7 to 2.65 billion year old calc-alkaline volcanics, associated volcaniclastics, and some minor Pegmatites. Specifically, the felsic rocks in this particular terrain are high field strength element enriched, which is thought, and it coincides with the juvenile crust. And that's another feature which we see associated with VMS occurrences. These felsic intrusives tend to be high field strength element enriched and are what we classify as F3 type. There's a paper out in the 1980s that basically defines those characteristics. But wherever we find those F3 rhyolites, we tend to find VMS deposits. Here's another map, just kind of zooming in on the specific area I did. Basically, all you need to know is King North and the King South deposit are hosted within essentially a green schist facies metamorphic volcanic sequence. And that the King North deposit is my sort of deposit study and is a long strike from the King deposit. Here's a better map that's going to be in the new paper next year, hopefully. Basically, this terrain was extensively deformed. We've got at least 4 different deformation episodes. Basically, series of extension followed by compression, and that there's a lot of granites in the local area as well. And the granites come in at around 2.6 billion years ago, and it's that what creates the metamorphism in the area, and as well as the regional sort of deformation. So essentially, we can metamorphose these up to about amphibolite grade, but most of these rocks are green schist. So there's a summary. We're in somewhere called the Ejudina domain. It's the Canalpi terrain is split up into several domains. That's basically where we are. So here's some core of the King deposit where we see some very clear, massive sulfide textures, some brecciated textures, and another thing that they're quite magnetite rich. And one of the 3 main questions I had at the time when I got given this project was if King North is a true VMS or it's one of those hybrid types, is it part of the same complex as the King deposit further south? And basically what controls the occurrence of copper and gold at King North? Because one of the curious things is that King North has a copper gold signature in one of its holes, but it doesn't have that in the other hole I studied. So I was wondering what controlled that. So what I did is I basically got given these rock chips and I did a bunch of thin section analysis, some scanning electron microscope work and some quantitative X-ray diffraction. That was to determine the alteration mineralogy. And what happens is obviously I've got those thin sections, I started to label them up. So at the top of the 2 holes I was given, say the first like 50-ish meters, it's a series of green schist facies metamorphics, quartz chlorite muscovite schists, and that I determined that the protolith was kind of more around the quartz and feldspathic area. It says mafic protolith on the slide, we're going to get to that. But in the SEM, we revealed quite a few examples of illite, rutile, or monazite. Illite being quite is a clay mineral, and so the clay minerals kind of indicated that these are quite strongly, intensely altered, and it's more likely to be sericitic alteration. We get some examples of epidote in here, quartz epidote, chlorite schist. These tend to occur in the middle where the actual ore body is, and I determine these to be kind of intermediate volcanics. And then as we get deeper into the bottom of the holes, we tend to get classic green schist. Actinolite becomes very common. Again, schistose rocks, green schist facies, get quite a few titanium oxides in here. as well. But it's really where the geochemistry came into it. Because these rocks are so heavily metamorphosed, you can't really determine what the protolith is very easily. But you can use trace elements to do that. And this plot here by Pierce is a great one, using zirconium against titanium oxide and niobium against yttrium. Basically, what we see is sort of three quite distinct sort of classes of protoliths, where we have these basalts, which occur at the bottom of the hole, this blue sort of, and these yellow sort of andesite basalts, sort of hybrid, and then obviously the rhyolites and dacites at the top as being they were at the top of the hole. We could separate them out further using thorium and cobalt. That shows that these volcanics were calc-alkaline trend dominantly. We did get one that was kind of off in the folio, but we interpreted that as a late stage intrusion. But what the point is that this geochemistry was really clearly telling us that we had at the bottom of the hole these sort of calc-alkaline basalts, at the top these calc-alkaline felsics, and in the middle where the ore was being hosted in the intermediate band. Now this plot, once we determined that, we wanted to look at the alteration, because the King deposit in the south is overturned, and the way you determined it as being overturned was looking at the alteration, because basically the most altered rocks were lying stratigraphically above the ore horizon, which is not what you expect. You expect it to be below. And so it was determined that deposit's overturned. So that was another question: is the King North deposit overturned? So on this plot, the yellow indicates the felsic rocks, which lie above the ore horizon. As you can see, they plot towards the top right-hand side of this plot. And that indicates that these are the most altered rocks, whereas the basalts plot very close to the least altered box, and therefore are, of course, least altered and represent the hanging wall. So once again, the footwall is basically above the ore horizon, and therefore this deposit stratigraphy appears overturned, just like the King deposit in the south. Another thing I decided to look at, ignore the red square, is that I managed to determine kind of what the tectonic setting was of this deposit, because the felsics and the mafics plot on this very clear trend in toward the continental arc type environment. So already I'm starting to think is that we've got some rift going on in the continental arc environment. That's verified by the mafics plotting in the sort of center here in this back arc field. So we've got back arc basin affinity mafics and continental arc affinity felsics. So straight away, obviously, we're dealing with one of these two settings, either a back arc basin or a continental rift back arc environment. And I settled in my masters on the right-hand side, the continental rift, although there is quite a lot of evidence that it could just still be a back arc, but was kind of quite an evolved back arc setting. Now, when my masters kind of finished, the company that I was doing this for done some more drilling. And what they found was another massive sulfide horizon further down in the holes, which is kind of direct evidence that we've had two sort of ore bodies in this sort of area. So I couldn't plot that on, but in here, this is essentially a plot of the two holes I'd done as well. The two holes I'd done were EC 175 and 164. They did a diamond drill kind of cross-cutting the 175, and then this other hole here was historical in 173. And what you can see, obviously, felsic volcaniclastics at the top, intermediates, then mafics at the bottom. A nice kind of simple stratigraphy. Now, one thing I didn't put on here was that the copper and gold anomaly is in 175 over here, whereas the lead zinc anomaly is in 164. And to explain that, I had to delve quite deep into the literature, and I managed to find an explanation that's a little bit complicated. But in essence, one of the observations I made was that we had a lot of magnetite and titanium oxides in the rocks which had the gold in, whereas we didn't see those rutiles, we didn't see those iron oxides as much in the EC164 hole. So what happens is in the magma chamber, if you change from olivine to magnetite crystallization, what you do is you remove the titanium, the iron from the melt, but at the same time, what you do is you reduce the sulfate to sulfur in the magma chamber. And that sulfur, that new sort of reduced sulfur combined to copper and gold. So basically that takes that out of the melt and into that sort of fluid phase. If you then remove that from the magma chamber and then place it higher up in the stratigraphy, you deposit gold copper related sulfides. And so that was the explanation I came up to explain that difference. But in essence, that explains that there. And then of course, we've got that stratigraphy, which I've explained. When I compared this to the King, it was virtually very similar. We had the quartz muscovite schists at both deposits. Alteration assemblies were very similar. The only thing that was a little bit different is that the deposit in the King South has garnets in, and that meant that it was kind of more amphibolite grade. So the grade of metamorphism is slightly different. And the reason for that is that the King South deposit is closer to the granites. And so that would increase the temperature and therefore make that a higher grade of metamorphism. So to classify this deposit, I made a sort of generalized stratigraphy and compared it to some of the bimodal, because it was quite obvious we had two types of volcanism here. And really the way you do this is if the host stratigraphy is more felsic dominant, you're supposed to call it bimodal felsic. If you've got more mafic, you're meant to call it bimodal mafic. I've kind of got half and half, but because the ore deposit was hosted mainly within the felsics, and we got intermediates, whereas the bimodal mafics don't have as much intermediate volcanics, I went for bimodal felsic. So to summarize, King North is a bimodal felsic VMS. It's an extension of the King deposit. The copper gold is controlled by the crystallization of magnetite. The immobile and high field strength element geochem kindly shows that we're in a rifted continental arc or back arc setting, and that we've got stacked VMS potential. Thank you very much for listening. If you are interested in more VMS talks, I host, I'm one of the hosts of Ore Deposits Hub. If you haven't seen those talks, I highly recommend it. This one was quite recent from Steve Piercy. It's absolutely brilliant. Well worth your time if you're into VMS. He's another very big expert. And then tomorrow, if you're really up early, you can watch live, basically my supervisor talk about everything I've just talked about, but better. So feel free to tune into that. I welcome any questions.
Right, thank you for that, Jamie. That was great. If people could put the questions in the chat and then I'll read them out.
I'll stop my share as well.
Safi, can I ask a quick question?
Go for it.
So you said that you kind of were deciding between, in your masters, between a rifted continental arc or a back arc basin to come down on. And I'm not sure if I missed it, but did you have any reasoning for which one you went for in the end? What was the kind of decision making in that?
Yeah, so mainly the geochemistry. So the mafics were a back arc basin affinity, and also I didn't show it, but the rare earth element plots, they are akin to back arc basin basalts when I compared it to some literature. But the sort of tectonics in the Archaean, and at this time, I felt like the overall tectonic environment was very much already in a cratonic state. And there's a lot of mantle plumes at this time as well. So if you put a plume into the continental sort of setting, you begin to rift it. And so I felt like with the general knowledge I had about the Archaean, as well as some of the geochemistry, like especially the felsics were continental arc related. I felt that was the more realistic option. But it's kind of hard to prove. And I think it needs a little bit more data, a bit more of a focused study. But a good question.
Cool. So it doesn't look like there's any questions in the chat at the moment. I'm sure if people want to keep putting ones in the chat, if anything comes up, then Jamie, if you want to maybe respond via the chat as well. If that's
yeah, I can do that.
Until you have
that's
to
no
go.
problem.
I think what we'll do in the just for kind of time purposes, we'll move on to our second talker this evening, or speaker this evening. So the next speaker is Finlay. So Finn did his integrated masters and undergrad at Oxford, and he did his masters under Lawrence Robb, he of the famous 2004 textbook, and did that in tin-bearing pegmatites in Namibia. He's now doing his masters at Cambourne in mining geology. So Finn, if you want to share your screen.
See that okay?
Yeah, all good.
Sweet. So just an introduction. Will just covered a lot of this, but I did do my 4-year degree at Oxford, and I'm now here at Cambourne School of Mines doing my MSc. And today I'll be presenting my master's project that I did last year, which is on the tin-bearing pegmatites in West Namibia, which was sponsored by a company called African Mining. And so a bit about the company. So the flagship asset of African Mining is this really big pegmatite hosted tin, tantalum and lithium deposit. It's got a JORC compliant resource of around 95,000 tons of tin, 6,000 tons of tantalum and around 450,000 tons of lithium oxide. And the idea is with these byproducts of tantalum and lithium, they'll be able to effectively produce tin for free once the mine is up and running. And it's not the only pegmatite in the area. So on the same mining license, they've got 180 mineralized similar pegmatites. So it really is an enormous deposit. And so the latest cash flow modeling suggests that the value of this mine is between 87 and 158 million pounds, depending on a 20% fall or a 20% rise in the tin price. And it's listed on ATO at the moment. And as of this morning, it has a market cap of around 20 million. So it's a pretty interesting investment opportunity if you're that way inclined. So my project was mapping a 30 km² exploration license with a focus on characterizing and delineating mineralized pegmatite veins within the license, from which I'd take grab samples, which I'd run through LAICPMS to get bulk geochemistry, perform a bit of petrographic analysis on them, and then coupling that with the field relationships of the pegmatites, try and constrain the relative ages and try and make inferences about their evolution. So really, to understand this project, there are three lithologies in the area you need to understand. So there's the monzogranites, the pegmatites, which in turn intrude into these green schist facies, metasediment country rocks. So the monzogranites, they're paraluminous in nature. Their bulk mineralogy is quartz, albite, microcline, orthoclase, biotite. And their accessory minerals include things like garnet, zircon, importantly monazite, I'll come to this later, and apatite tourmaline. And then the metasediments, they belong to the Amos River Formation, which is green schist facies, metamorphosed turbidite sequence made up of biotite schists and metamols interbedded. And yeah, it's been subject to some ductile deformation, but there really isn't that much that's structurally interesting about the area. And where they've been intruded by pegmatites, they've been subject to alteration, most significantly tourmalinization. So that little micrograph at the bottom left there illustrates some of the alteration of the schist wall rock, where sort of boron-rich fluid is leached into the rock, removed the iron from the biotite, and precipitated this tourmaline. And so the pegmatites, there are two variations which are broadly classified based on whether they're mineralized or not. And so you have the garnet tourmaline, which, like their name, contains garnet and tourmaline. They're hosted by the granites and the metasediments, generally non-mineralized, contain some alteration and have a crude zonation within them. And they're illustrated by the schematic on the left there. And then the other type, which is the mineralized tin-bearing pegmatite, niobium tantalum tin, is exclusively metasediment hosted. It's mineralized and usually heavily altered by means of Greissenization, and is characteristically unzoned. And so just from the field mapping, you can see that the different pegmatites are distributed in a sort of characteristic way in the mining license. And so you have these large granitic bodies like this one on the right, which are sort of mantled by these concentric garnet tourmaline pegmatites. And then you get these mineralized pegmatites, which are generally further afield from the granite. And so if you look at these key mineralizing key minerals like tin and coltan or tantalum, you can see that the pegmatites, they generally get richer in these key ore forming elements as you get further from a granite body. And so using that, you can sort of start to come up with this hypothesis for the generation of these pegmatites and what their source really was. And so perhaps during the sort of the partial crystallization of a granite, you had this concentration of fluxes like water, boron, and fluorine, which allowed a pegmatitic melt to sort of exsolve from the parent granitic melt, which would in turn hydraulically fracture the country rock and utilize the granite's thermal aureole to propagate further and further away from the granite body, until at these sort of late stage, in the late stage pegmatites, you'd get the concentration of these incompatible elements like tin and tantalum and niobium. And so these are just a couple of pictures of the types of mineralization that you'd see in the mineralized pegmatites, with citrite sort of highlighted there. And so to test this hypothesis, you look at fractionation patterns. And so without going into too much detail here, the ratios of certain elements change depending on the fractionation state of a granitic melt. And so you'd expect zirconium and hafnium ratio to decrease as your granite became more and more crystallized, and tantalum to niobium and rubidium to strontium would increase. And so you can model these based on the bulk partition coefficients of various elements. And so the lines there, the CL and the CS, are modeled concentrations of these key elements within a liquid, and the CS is concentrations of these elements within the crystallizing phase. And by and large, all of the points, if the pegmatites were sourced from a parent granite, they should all sort of form a sort of band between these two lines, which by and large they do, with Ng denoting the parent granite is an M member, whereas the mineralized pegmatites, which are the blue points, is another M member, with these garnet tourmaline pegmatites forming a sort of intermediate. And so with rare earth elements, you'd expect usually, because generally they tend to be incompatible in granitic melts, you'd expect them to become more concentrated with successive fractionation. But in fact here, you actually see the opposite. And so these blue lines are the mineralized pegmatites, whereas the red lines are the granites. And you can see that the pegmatites are significantly depleted relative to the chondrite in terms of rare earth elements. So you have to reconcile this with the results that we've seen and try and come up with an explanation for it. And so here it just shows a few partition coefficients for different rare earth elements for different minerals or accessory minerals. And I really want to draw attention here to the monazite and the apatite here. And so because they have such high partition coefficients, even a really, really small amount of these minerals in the parent melt would mean that the concentrations of rare earth elements decrease with successive fractionation. And so really that explains why these late stage pegmatites are depleted in rare earth elements. And so you have to address the other side of the argument as well, right? So there's one explanation that these pegmatites are sourced from a parent granite, and there's another explanation that they were just sourced by partial melting and didn't necessarily come from a parent granite. And so usually if a pegmatite was from an anatectic source, you'd expect to see no sort of association with nearby granite bodies or anything like that, which we do in this case. You also wouldn't expect to see sort of chemical zonation in pegmatites spatially, which we do here. And also generally with pegmatites from an anatectic source, you'd expect them to be very small, which just really isn't the case at the Weiss pegmatite, which is enormous. And another thing you might look for is migmatites, right? So the actual site where this pilitic source rock might have melted, which you just don't see in the area. You just see these sort of green schist facies, schists, but no real sort of massive partial melting. And so as a conclusion, sort of presented this argument that the pegmatites came from this parent granite, but I have to point out that my conclusion might not really be applicable to all pegmatites in the area. And so I only really looked at 30 kilometers squared license, whereas the actual Weiss mine pegmatite is about probably 30 kilometers away from this license. And yeah, and again, it doesn't necessarily rule out the origin from direct anatexis. It could be that the pegmatites came from a migmatite, which was sort of using the granite's thermal aureole to migrate. And you know, to get real concrete evidence for the timing and the evolution of these pegmatites, really what we'd look for is the age. And so you can date cassiterite, you can date zircons, which are found in the granites. And if we can find the relative ages of those pegmatites in the granites, research, we can really figure out where they came from. So that, yeah, that's me done. Open to questions.
Oh, thanks for that, Finn. We do have a question from Sam, who's asking, how did you fairly sample the pegmatites for the laser ablation mass spec? He says, surely that's quite difficult when pegmatites tend to be strongly chemically zoned. Yeah, that's a really good question. So pegmatites, they're characteristically megacrystic, and so you can find sort of feldspar crystals that are the size of your head in these things. But because these pegmatites are zoned, the wall rocks tend to be much finer grained. And so the pegmatite samples that I took were from what are called these aplytic zones at the border of the pegmatite, which are sort of granitic in their grain size, if you like. Because obviously taking samples from just like one piece of feldspar, it wouldn't have been representative of the whole pegmatite. And we have another question who's asking about methods. Why did you use laser ablation mass spec and not XRF? And was there a risk of saturation of detectors with such concentration difference between major and minor elements?
Sorry, could you repeat that question?
They've asked, why did you use laser ablation mass spec and not XRF? And was there a risk of saturation of the detectors with such concentration differences between major and minor elements?
To be honest, I don't know how to answer that question. It's just what my supervisor recommended. So I'm not going to make a fool of myself and try to answer it.
I can ask a question. Obviously, as I'm still here. Good talk there. Quite like the little maps you made. You mentioned about the geochron, and I noticed you didn't mention dating the monazite. You could date the monazite with, I think, uranium lead. And I thought I'd make that suggestion. So I was just going to say, what would be, if you was to go and date the various sort of minerals that are present to try and obviously ascertain which model of formation it is, what would be like your kind of process for doing that? What would you look for? What specifically?
Yeah, so finding things to date in pegmatites is quite difficult. But with the mineralized pegmatites, there are cassiterites, which by one way or another, I know you can date. You brought up monazites as well, which again, you can date, but although they were present, they weren't present in sort of large amounts. So it'd be quite difficult to separate enough monazites from, you'd have to take loads and loads of samples basically to separate the monazites to date. So I would go for zircons contained within biotite from the granite to date the granite.
Yeah, that's good. I mean, the laser might help you because that's got really good spatial resolution. So you can zap them, and that should hopefully, if you've got enough present, maybe give you a good ratio that you could then use to date. And if you dated the monazite, that may date the fractionation, etc., etc. So, but it's good work. It's good.
Cool. Brilliant. Thank you, Finn, and to Jamie as well, both for your talks. They've been fantastic and a really good way to kind of start off the seminar series. I'm just going to put a link into the chat for everyone. It's got a link to a Google form, which is just a feedback survey. If you are interested in just giving us some feedback on how it's run this evening, it can be anything from how you found booking the tickets all the way through to any kind of constructive feedback for the speakers that you might want to give. And we would really kind of appreciate it as we go forward with the talks. We have got a few more talks coming up this term. We've got one every Tuesday until early December. They're all on completely different topics. So obviously this one was focused on ore geology and exploration, but we have got ones covering climate, seismology, fossils, a whole range. So do check out the website or look out for more of the Facebook events if you found us through that. Other than that, I just want to say again a massive thank you to Finn and Jamie for coming along, and thank you to everyone else for kind of spending your Tuesday evenings with us as well. And we hope you enjoyed it, and hopefully we will see you guys all again soon at some point. If you have any more questions, feel free to send us an email. We've got an email or Twitter on the website as well. So thanks very much, and hopefully we'll see you all soon.
Yeah, thanks, Safi.